Now let's talk about some of the practical considerations of insulation systems. The manufacturers and the suppliers of insulating materials can provide all sorts of technical information on their product and can offer a lot of technical application assistance in developing and adapting their product to your particular application. And by all means, you ought to take advantage of this service because it can save you a lot of time and expense in developing the system that meets the particular needs of your market, your manufacturing facilities, and your processes that you desire to use. At the same time, though, however, there are such a variety of materials and systems that are available that it causes a dilemma which is not necessarily easy to resolve because one has to zero in on all of the previously mentioned aspects of the problem in developing the approach that you decide to take. But you also have to look at the practical elements of the equation because frequently these are overriding. Now, a rewound machine is generally required to pass the standard NEMA high-pot test of twice rated plus 1,000 at 60 hertz for 1 minute, or the DC equivalent. This test is administered after the winding is complete, and failure at this point is expensive to correct, especially if the winding has been vacuum pressure impregnated with a high bond strength resin. And in order to have the best assurance of passing this final test, often the in-process tests are at successively higher voltages than the final test. And historically, practice has been used, starting out with the highest high-pot test at the bench level after the coils themselves are completed. And then it is successively reduced as the in-process test and the winding of the machine proceeds through the shop. For instance, after wind before connect, another high-pot test is typically used in order to assure that the winding is still has its insulation integrity before proceeding along the line of applying more labor to the winding and then have to undo it later. At the same time, typically surge tests are made in order to assure that the turn insulation has not been damaged in the process. Now, this philosophy was developed around insulation systems that had basically high dielectric capability in the form of the coil as it was installed in the machine. The old flake mica insulation systems, the film-backed mica paper, has inherently high dielectric strength. So these in-process tests are essentially no problem for a system or a coil which has not been damaged and has been properly made and treated during the manufacturing process. Unfortunately, some of the other insulation systems, such as the B-staged epoxy or the porous mica systems, do not have the inherent withstand capability of these other systems, and they cannot be tested at as high voltages during the in-process phase of the manufacturing cycle. Now, this bothers some people because they have not developed the experience and the confidence to feel that the windings tested at lower voltages are going to be able to pass the final high-pot test when the winding is completed. Also, the insulation at this state is in relatively weak mechanical condition and is therefore more vulnerable to damage during handling in the winding process. The way around this, of course, is to use a fully cured or a film-backed system. Both of these approaches solve the problem, but they create another one. For instance, a hard, relatively inflexible B-stage coils may be difficult to insert in the machine, and film-backed insulation may have more mechanical and dielectric strength, but the film makes the impregnation more difficult, especially if a wrapper is used instead of tape. Tests have shown that the breakdown strength of coils insulated with film-backed or porous mica paper is about the same after VPI treatment and curing, but before treatment, the film-backed coils have a much higher withstand capability. There is some opinion that the VPI porous mica system is more durable and has greater capability than the film-backed system after VPI. Before reaching such a conclusion, however, one must make sure that the comparison is based on real facts in similar situations and quality. Therefore, practical compromises for testing must be worked out based on the supplier's recommendations and the shop's experiences. Now, for B-stage coils in the green or the uncured state, they generally are not high potted at high AC voltages because the uncured resin has a very high power factor, and the heating that is resulting from exposure to high pot voltages can cause runaway thermal conditions which can damage the insulation and cause failure. To demonstrate what this dielectric heating can do to the coil, here's a picture of a coil which is puffed up due to the losses generated within the insulation system when it was subjected to high voltages, and it broke down the epoxy resin and caused the type of damage that you see here. Another practical consideration is the use of wrappers versus tapes. Wrappers have the advantage that for insulating the slot portion of the coil, it's less labor intensive for a given amount of insulation, and test results show that wrapped coils generally have superior mechanical and electrical properties over coils made with tape. Now the wrapper is applied, as we see here, as opposed to the tape, which requires multiple layers of tape, which is generally applied in the half-lap manner. Now, we intuitively feel that the wrapper has some advantages over the taped insulation system, and I'd like to share with you just some information that was published in IEEE paper which quantifies your intuitive feelings. This was a paper entitled The Influence of Mica Tape Application on Insulation Characteristics of High Voltage Rotating Machine Coils. It was published by some engineers from the Toshiba company in Japan. They reported on the properties of the mica paper insulation produced with the same material, only applied in various widths. They also investigated the properties of the insulation produced with the same materials, but with tapes applied with various techniques, half-lapped versus butt-lapped. And for these tests, the paper that they used was porous mica with a 17% resin content. Most porous mica materials that we use in this country generally range in the 10 to 20% resin content category. What they did was to make up several samples and tape it up with the same type of material, the same number of layers or half-lap layers of tape, and the equivalent number of wrappers. And they measured the capacitance of the winding during the vacuum pressure impregnation process. And the idea here was, as the resin displaced the air in the winding, the capacitance would change, and when you get to the point where the capacitance doesn't change anymore, that would indicate that full impregnation has been reached. Now, we didn't show all of the data that's available in this report, but we're looking selectively at tapes varying in width from 0.4 of an inch to 3 3/4 inches, and comparing that to a wrapper. Now, if you look at the A section of the curve, which is the vacuum cycle, for the first few hours, the capacitance doesn't change because it's in the normal vacuum extraction process to remove the air and the volatiles from the system. At that point, the B part of the cycle starts where the resin is admitted to the system and starts to penetrate the insulation, and the capacitance starts to increase. And then finally, after the soak at atmospheric pressure, the pressure is increased to approximately 100 pounds per square inch, as in the typical VPI cycle, and completes the impregnation process. Now, the interesting thing to note here is that the narrowest tape impregnates the fastest, as you can see, because it reaches its final capacitive level and then levels off at a fairly short period of time. The 1-inch wide tape, which is typically what we would use for insulating coils, is somewhat slower, And then, of course, the wrapper appears to be in about the same time frame as the 1-inch tape. The wider tapes impregnate at a slower rate, primarily because the tapes are applied tighter than the wrapper just for practical reasons. And the wrapper, even though it has fewer joints, because it is applied less tightly, it is more impregnable from the ends because of the wider spaces available. The point here is that it relates the impregnation rate to the number of edges in the tape. The narrowest tape having the fewer edges, and of course the wrapper having the most edges. And the point that was made in the paper was that even though the porous tape was used, most of the impregnation was occurring through the edges and along parallel to the surfaces of the tapes and not actually through the tape. And I think that's a concept that is important to remember. Now, they also took these same samples after they quantified the impregnation rate, and they ran tests on them, various mechanical and electrical tests, to demonstrate how the properties varied depending on how the tape was applied. I think the voltage endurance characteristics shown here, as well as the voltage breakdown characteristics, typify the results of the test. The top curve there, the 15 kV voltage endurance test, was ran on samples with 5 half-lap layers of tape or 10 wraps and then VPI'd, not unlike what might be used for a 4160-volt system. And as you can see, the voltage life characteristic increases with the width of the tape, which means that there are fewer edges. The weak part in the system, as you would intuitively expect, would be across the edges. So the wider the tape, the fewer edges, the better the voltage endurance characteristics are. This is equally true with mechanical characteristics, because the edge is usually the initiation site for the failure, whether it's fatigue or fracture or whatever the failure mechanism might be. After it gets up to the wrapper width, of course, it levels off, and as you'd expect. Now, the other three curves are not voltage endurance, but the breakdown voltage, the short-term capability of the insulation, which is relevant to our discussion for the in-process high-pot test. Again, we're talking about samples insulated in a similar fashion. The A curve is unimpregnated with 5 half-lap layers of tape or 10 wraps, and the C curve is the same application, only before it is VPI'd. And you can see there's a considerable difference there as far as the capabilities. Also note that the variation with the width of the tape is much less in this instance, because the inherent properties of the system have not been fully developed in the unimpregnated state, and the breakdown voltage mechanism is a little bit different than the voltage endurance mechanism. But the point is that the unimpregnated capability is only in the range of 25 to 30% of the capability of the system after it has been vacuum pressure impregnated in the normal fashion. Another interesting conclusion that can be drawn from these test results is that they also ran some experiments where they used properly half-lapped layers of tape, properly meaning that the lapping was relatively precise, and the edges of the tape were registered such that the edges did not line up in the multiple layers of tape. And as you would expect, if you do register the edges, even though the laps are as they should be, the capability of the poorly lapped and registered tape is not as good as the application in the desired fashion. Their tests showed that the properly half-lap specimens had voltage life about 60% better than samples where the edges were lined up, and the short-term breakdown capability was almost 20% greater on the same basis. So this points out the importance of machine taping and also the importance of quality control so that the coil makers are putting down the tape half-lap but also registered in the proper manner. Now these considerations are important whether the repair shop makes its own coils or it chooses to buy them from another coil shop. The quality and the register and lapping of these tapes has a very significant impact on the quality of the coil. And it should be pointed out that the fewer the layers of tape, the more significant these variations become as far as its mechanical and electrical properties. Now, let's go on and talk somewhat about the varnish or the resin treatment of the windings. We've just got through demonstrating that the properties of the material are considerably enhanced by the impregnation and curing of the resin in the VPI system. And we've at length discussed the importance of the properties of these binder materials because they are, in the end, the key to the properties of the insulation system that we desire. The composite insulating materials that we've been talking about must be impregnated with a resin in order to bring out these final properties. And the resin that we use will determine whether it's Class B or Class F or Class H. There is no one best answer for all insulation application problems. You know, a VPI system for in-shop application is fine, but it's not suitable for on-site installation where VPI facilities are available. And conversely, a good on-site system may not be the best available for in-shop use for practical or economic reasons. But they both must be capable of withstanding the multi-stress environment that we've discussed at length, the mechanical, electrical, thermal, and chemical environments that the insulation must operate in. For many years, many thousands of machines were successfully wound with machines using the dip and bake process. And that system is still used today in a great many applications, although it certainly is not state-of-the-art, and it is rapidly being replaced with vacuum pressure impregnation or other processes and system treatments in order to develop the superior systems that these technologies and materials make available. Now, a key objective of the makers of a modern insulation system is to produce a void-free system. And void-free is especially necessary for high voltage applications because deterioration of the insulation due to internal corona is a very serious failure mechanism to be reckoned with. But it is also very important for even the lower and the medium voltage machines because if it's void-free, it means that you have better heat transfer between the conductors and the cooling medium. And you also have assurance that the conductors are in fact tightly held and bonded together in order to avoid some of the mechanical problems that we've been discussing. Now, to produce a void-free insulation system, the resin must be completely fill all of the small spaces in the composite insulating materials as well as filling the small interstices around the conductors themselves. 100% reactive resin should be used because you do not want volatiles entrapped in the insulation system that can create voids. Now, given that the objective is to make a void-free system, there are several but still limited ways to achieve this objective, and all of them involve the resin treatment. The first is to apply a surplus of resin during the application of the insulating tapes that we've previously discussed. The second is to use a resin-rich insulating tape or wrapper that has been pre-impregnated with a resin, the B-staged approach. And the third is to use vacuum pressure impregnation to force the resin into the composite to impregnate it with a resin after it has been applied. Now, all of these processes will produce good windings, and they all have advantages as well as disadvantages. But the key is to use a good solventless resin that has good electrical and physical properties. How we get that resin into the insulation system is less important than the quality of the resin itself. Now, the chemistry of the resins, and therefore the final properties of the resin, is to an extent determined by the physical properties that the resin has in its uncured state, which has to be adjusted to accommodate the processing variations. Now, for instance, in the brush-in method or the B-staged method, the resins are applied or impregnated into the composite when the material is still in the unapplied form, so that we have an assurance that the material is being built into the system as it's being layered up. Because it is in this form, there is more flexibility as far as the selection of the resin properties, in that one does not have to be concerned with the viscosity, which is a preeminent requirement for vacuum pressure impregnation capability. What I'm trying to say is that the molecular weight of the resins has a great effect on their final properties. And in the B stage or the brushed-in approach, one does not have to be concerned with compromising these properties in order to come up with a low viscosity material that will penetrate through the multiple layers of insulation to give the final properties. Now, the resin system ultimately selected is based on a series of compromises, not the least of which is the one we just discussed. For instance, the curing agent used may give the desired time and temperature of the curing cycle, but it also has an impact on determining the heat distortion temperature and the dissipation factor characteristics of the final material. Similarly, high bond strength is desirable because we're trying to produce a durable, rugged mechanical structure. But at the same time, if it's too high in bond strength, it often means that it's too brittle, which means that it is susceptible to cracks if it is stressed unusually high for the capability of the system. But no insulation discussion would be complete when we're talking on the subject of resins without getting into the somewhat controversial subject of a polyester versus epoxy resin for VPI purposes. This subject is generally not an issue for resin-rich or B-stage systems, because in these situations epoxies are generally used, but for the VPI the issue versus polyester and epoxy is a very real consideration. As for most situations, there are advantages and disadvantages both ways. Given a certain set of requirements, one could effectively argue for either one of these generic types of resins. Actually, there are some polyester resins that are better than some epoxies, and conversely, there are some epoxies that are better than polyesters. It depends on which one you're talking about. Now, when trying to compare one resin to another, it gets somewhat difficult because the manufacturers and the suppliers of these materials have data sheets that often present data on similar properties but measured in different ways and under different conditions. So one finds it rather difficult to come up with a combination of data or application sheets that supply information that allows a one-to-one comparison. That makes it more difficult for the user because he must then either run some tests himself so he can get the one-to-one comparison or rely on published data. to come up with the same type of information that he needs to make his conclusions. Now, let's just look at some of the basic properties that are compared in making this evaluation of epoxy versus polyester resin. The first one we're going to talk about is the heat distortion temperature. And the next couple of slides we look at, we're going to present just some of the principal properties that are frequently discussed. And what I've done here is to try to take data reported from different sources so as not to slant it one way or another depending upon what somebody may have been trying to prove or the point that he was trying to make. But there is common agreement that the polyester resin normally has a lower heat distortion temperature than the polyester or the epoxy. You can see the 85 versus the 105 degree difference. And what I've done here also, I should mention, is pick a good epoxy and a good polyester so that we're not comparing the top of the line in one case versus the bottom of the line in the other. Bond strength is directly related to heat distortion temperature in most cases. And just for comparison, let's look at the bond strength of these two different types of resins as tested by two different standard ASTM tests. In one case, reported by source number 1, the polyester is 5.8 versus 16 for the epoxy. And another ASTM test, it's 410 versus 1500. The ratio is still in a range of around 3 to 1 or so difference in bond strength. However, as I pointed before, bond strength is a two-edged sword. You want high bond strength, but if it's too high, then if the build of the material is too high, it becomes vulnerable to cracking. And because of its high bond strength, when it cracks, it can also crack the insulation composite materials underneath. Another key comparative point is weight loss, because being an organic material subjected to high temperatures over a period of time, it does lose weight. And obviously one does not want a material which is going to suffer great loss of weight during the normal life expectancy of the system. And here again we find some differences but also some similarities. Source number 1 ran a test at 200 degrees centigrade for 1,000 hours, and the weight loss was 4.2% for the polyester versus 5.5% for the epoxy. Source number 2, 200 degrees C at 168 hours, 13% for the polyester versus 2.3% for the epoxy. And another test, not doing it on the same basis, but rather saying how long or at what temperature would it take to lose 5% of its weight in 20 years. And in this case, we have 136 degrees centigrade and 154 for the epoxy, and there's not that much difference in that case. Now, dissipation factor is another key measure of the dielectric or the electrical properties of an insulation system. And here are some numbers on resins used to VPI some form coils and tested under a similar fashion. This is from source number 1. At 55 volts per mil at 25 degrees centigrade, 130 and 155 degrees centigrade, you see that the polyester is substantially better than the epoxy. That's one set of comparisons. Now let's look at another one. The chemical resistance is also a very important factor because many machines are operated in environments that are less than passive. This aggressive and conducting chemical situation that we were talking before. Now, most resin suppliers will supply data sheets with all sorts of information on resistance to a wide variety of different chemicals that a machine is likely to encounter in practice. And it's not strictly true, but on the other hand, the variation in resistance to polyesters and epoxies when exposed to oil and some of the solvents and a lot of the rather innocuous things are not really that much difference. There are some differences, pluses one way, minuses the other, but nothing outstanding. But there are a few chemicals which there are drastic differences in the ability of these two classes of resins to withstand. One is the exposure to caustic solutions or basic solutions of sodium hydroxide. Vendor or source number 1 reported that when exposed to 10% solution of sodium hydroxide, both types of resins were seriously degraded. Another one indicated that when exposure to the same concentration for 90 days, looking at a weight change basis, the polyester wasn't in the picture and the epoxy only increased 1.1%. Another independent investigation showed that when exposed to 25% solution of sodium hydroxide, the weight change, which is a measure of how much the contaminant is absorbed into the resin body itself, was 14:1, where the polyester weight increased 14 times as much as the epoxy, which is a significant ratio in itself. So these data would suggest that epoxy resins are more resistant to degradation caused by caustic solutions such as one would experience in paper mills where black and white liquor contamination is a problem with some types of machine. Another very clear-cut differentiation between the two capabilities is if the machine is going to be used in a hermetic application where the refrigerant is Freon, then the polyester stands no chance and is quickly degraded by the exposure to Freon when the epoxy is essentially unaffected. Now another comparison that we should look at is what happens to these materials when exposed to radiation, because this is not a common type of exposure and contamination, but I think it also tells some important stories about the capabilities of these materials. In applications for nuclear power plants, for instance, these considerations are very important, and I'm not suggesting that they're important for day-to-day application in normal utility or industrial environments, but also I just use it to point out that it is another measure of the capabilities of the different resin classes, and it tells an interesting story. For instance, the dielectric strength of the materials as tested per an ASTM test shows that initially, and this is true in many epoxies and polyesters, the dielectric strength of the polyester is somewhat superior to the epoxy. And after exposure to radiation, this property for polyesters improves while the capability of the epoxy decreases. And dissipation factor, as measured on vacuum pressure impregnated form coils, before exposure to radiation, you can see the numbers there. The polyester had a 21.5% dissipation factor. The epoxy was 46.6. And after exposure to considerable radiation, the dissipation factor of the polyester actually got better, less than half of what it was initially, where the epoxy got worse. And the helical bond strength test showed that even though the polyester had less bond strength initially than the epoxy, as we've previously seen, but after the test, after exposure to the radiation, the bond strength of the polyester improved while the bond strength of the epoxy decreased. Now, this is not to suggest that one or the other is superior for the overall application requirements in industry. It's merely to point out that there are some significant differences, but there are also some very significant similarities. And it is not fair to paint either system with a black brush when it you have to look at all the different variables that must be considered. Now, one of the other considerations which is very important is the economics. And nobody can discount the importance of the economics in making decisions that involve the type of cost that could be related to the development and maintenance of a vacuum pressure impregnation system. It's pretty well established that the cost per gallon or per pound of polyester resins is less than epoxies. On the initial cost basis, that obviously is a big plus. But on the same time, the maintenance of the properties of the resin, the polyesters have traditionally been controlled more easily than epoxies. Now, two of the key properties that must be maintained in the resin system for vacuum pressure impregnation is the viscosity of the resin and its gel time. The viscosity is important, as we've already said, because the more fluid the resin, the more able it is to penetrate through the multiple layers of material and get inside and do its job. Gel time is important because, one, you want the resin to cure up at the prescribed time and temperature once you have impregnated it, but you don't want the gel time to decrease and get short enough to the point where it can kick over and cause the resin to solidify in the vacuum pressure impregnation tank or the reservoir. And typically, in the past, these properties have been more economically controlled with polyester resins and epoxies, for the simple reason that inhibitors or accelerators could be added to the polyester resin to control the gel time, and reactive diluents could be added to control the viscosity. In order to control these properties of the epoxy resins, it was necessary to add fresh resin to the makeup of the system in order to keep these key parameters under control. Now, in a large shop or an OEM, which is processing many machines, you have to keep adding fresh resin just as a matter of keeping the tank full, so to speak. So you automatically took care of these concerns. But in a repair shop that uses a lot less resin by nature of the fact that it is processing fewer machines, you don't need to add so much makeup resin so that it is a more serious problem in controlling the viscosity and the gel time. And you have to either accept the fact that it's gradually going to change, or you have to do something about it. Now, recently there's been a lot of work done so that the epoxies are controlled in the viscosity sense by adding reactive diluents, but there is a limit to how far you can go here, because too much reactive diluent changes the properties of the finished material, and that's true in polyesters also. So you can't just keep adding reactive diluents without something happening that compromises the properties. So although the OEMs were the first generally to use vacuum pressure impregnating of their windings, and they started out using epoxy resins, and they probably, I shouldn't say probably, you can be sure that they went through a very detailed and disciplined evaluation of all factors, including the economics, in arriving at the decision that they did to use polyester or the epoxy resin as their preferred choice. Now, the repair shops got into the business after the OEMs, and this is where the options became more into play, and some repair shops opted for polyesters and some opted for epoxies, but there are some distinct economic advantages for the repair shop from the epoxy viewpoint. Now, that is only a viable argument if it provides a product which is responsive to the needs of the market. If your key customers say, I don't care what you say, if I want polyester, or conversely, if I want epoxy, you have to be in a position to supply them one way or another. And although a lot of the OEMs selected epoxies initially, some of these OEMs, same OEMs, selected polyesters for different product lines after going through similar detailed evaluations, such as for DC armatures and high-speed applications and some other applications where the properties and the characteristics of the polyesters obviously gave them the results that they wanted instead of the epoxies. In addition, the polyesters have been qualified for some very difficult applications, such as Class 1E hazardous locations, which is about as difficult an application as anybody can find. And of course, the epoxies qualify for this application too, so you may have a standoff when you look at it from that viewpoint. I guess when it comes right down to the end of it, though, although this choice may be complicated and difficult, where lots of different variables have to be considered and weighed in making the decision, there's no question that the VPI process itself is still vitally important. And I guess you could say I'd rather have a winding which is properly impregnated with a lesser resin than one which is poorly impregnated with the best resin available, depending on what standards that you want to measure it by. Because if you end up with a situation like this, where you have all sorts of gaps and voids where the resin either hasn't gotten into the system or it hasn't stayed there, it's run back out during curing or something, then you end up with a situation which is less than what you started out to achieve. So now let's talk a little bit more about the temperature or the thermal considerations for insulation systems. As we previously said, the IEEE standards limit the allowable temperatures for different classes of insulation. And the selection of the materials for the development of the systems must recognize these requirements. And the temperature rating of the material by itself is only part of the equation. The properties of the inorganic materials, as we've said before, are essentially unaffected, but the properties of the resins are going to follow the 10-degree half-life rule or the Arrhenius equation, as we've mentioned several times before. And this applies to all organic materials, whether you're talking cotton or that used to be used in some insulation systems, or whether you're talking the more sophisticated high performance materials such as Kapton and Nomex. They still follow the same basic rules. Now, the expected life of windings supplied by the repair shop can be shortened due to unexpected temperature effects. This may be caused by the use of materials that do not have the necessary thermal capability, or the machine may operate at higher temperatures than expected for several different reasons. The latter may occur because of improper repair procedures or failure to correct previous damage to the machine that can result in increased losses, primarily the iron losses in the stator core or the rotor core in some instances. The shortened life may lead to warranty claims or damage to a shop's reputation, and it is important to understand and identify problems caused by the accelerated heat aging. A recent TAPI paper entitled Pulp-Coated Motors, The Effect on Motor Life, was published by several gentlemen from a major paper company and the General Electric small motor plant. TAPI, by the way, stands for the Technical Association of the Pulp and Paper Industry, if you're not familiar with that. But what they were looking at was getting back to the idea that we mentioned initially, that the normal expected life of a winding is in the 20 to 25 year range, but they were experiencing failures in a much shorter period of time, 2, 3, 5 years, where everything would indicate that under normal operating conditions, the motor should go for the normal life expectancy of 23 years. So the question becomes, why is this happening? And is there anything we can do about it? Well, they took some motors and they actually ran tests. They coated the motors with pulp from the mill to block and cover the cooling passages. They partially obstructed the air intake to the fan enclosure and did various things to determine the impact on the temperature rise of the motor while performing its normal intended function. And they used a very interesting example to demonstrate the point that I'd like to share with you. They used an example of an actual scenario that you could very easily develop in a paper mill, where you take a machine and you put it in service in the normal application, and for the first year or so that the machine is operating, it's operating under essentially normal conditions with normal temperature rise. And then as the machine is in service, it's gradually accumulating pulp which is flying around in the air or maybe spilling from a piece of equipment which is malfunctioning or whatever. So it becomes coated with pulp. And for the next year, you assume that the temperature rise of the winding was increased 10 degrees. And then as the machine continued to be exposed to this environment, for the next 2 years, it had a light coating of pulp on its cooling surfaces, and the fan passages were partially blocked, and the temperature rise was 20 degrees centigrade. But then somebody come along and they saw that there was a blockage in front of the fan, so the guy kicked away a pile of pulp, and for the next 9 months the air was opened back up again, but it had developed a heavier coating of pulp, and the temperature rise was up to 30 degrees over normal. And in the final 3 months of operation, the motor had a heavy coat of pulp, and the air passage was partially blocked again, so that it was operating at 40 degrees over normal. And the motor failed after 5 years, and this is the life history of that machine during that 5-year period when this motor was supposed to have lasted 20 to 25 years. And an interesting way of looking at it that they present in this paper was the effective insulation life expended. And the equation is given there, and we won't go through it piece by piece. But what it points out is that this 10-degree half-life rule, the Arrhenius equation, can be reduced down to a useful equation that relates the expended life of the insulation at various temperatures. And as you go across, you can see the first year, under normal conditions, it used up 1 year of life expectancy. In the second year, when it was running 10 degrees hot, it used up 2 years of life expectancy, and so forth all along, until at the end of this 5-year period, because of the excessive temperature pattern, it used up 20 years of expected life in 5, and the machine failed. But you can take that same scenario and hypothesize that after that 5-year period, the machine failed, and it was sent to the shop to be repaired and rewound. And it was. And you can also hypothesize there were some things that happened to the motor during normal operation or in the failure mode or during the repair procedure that damaged the stator lamination insulation, which caused the machine to run a little bit hotter just based on that damage alone. The core loss was increased, so the no-load temperature rise was increased and assumed 15 degrees centigrade. And that's not a wild assumption, because you can take some of these machines that normally operate with a 15 to 20 degree no-load temperature rise, and you double the core losses, which can be proven to happen quite readily, and now you're up into the 25 or 30 degree temperature rise at no load. And as we'll see, that also applies to the full load operating points. So if we go through the same scenario as above as far as exposure to pulp and blocking of air passages, and we go through the same arithmetic, we see in the first year, even though it's operating in normal conditions, because the temperature rise is 15 degrees higher for these other possible reasons, the first year uses up 2.8 years of its expected life. In the second year, 5.65, and you can go on through to the point which is really just playing with numbers that says that in 5 years you would use up 60 years of his expected life, and of course that won't happen because his expected life is only 20 to 25. And the point of the matter is that the normal insulation life would have been used up in about 3 years. And obviously a premature failure would have occurred. And this gets back to some of the things we mentioned in our initial comments about rewound machines lasting a fraction of the time of new machines. And I think you can use this type of a scenario, obviously not the only one, but this type of scenario to develop a rationale and an understanding of how that type of thing might happen. Now we'd like to talk some more about the mechanical considerations, because as we've said all along, mechanical being the primary cause of failure, and we've set out in the beginning to define our insulation system as not only the insulation on the coils, but how the coils are wedged and tied and blocked, and how they are secured in order to control the vibration during normal and starting conditions. Remember again, we talked about those 120 hertz forces causing the windings to vibrate, and these accumulate at the rate of about 10 million cycles a day. And the accumulated looseness of the wear created by this vibration allows and causes the wear rate to increase until failure occurs. Now let's take a more detailed look at some of the forces that we're trying to protect this winding against, because I think they are quite significant in that we can relate quantitatively some of the things that we've been talking about that we have intuitively accepted. Now the vibratory forces acting on the coil and the slot may be calculated by the equations shown on this next slide. The equations given here are quite common in the literature, and we have a force on the top coil and we have a force on the bottom coil, and the maximum force occurs when the top and bottom coils in the same slot are in the same phase. But you can see that the force is given in pounds per inch of length of the coil in the slot portion, and it's a function of the square of the current and the number of turns. It is also influenced by the width of the slot. Now let's take that 200 horsepower motor that we originally talked about in developing the rewind rationale for how we would accommodate new insulation systems with the given parameters that we were trying to establish, and some of the pitfalls that could happen if we didn't recognize some of the ways the machine inherently cools itself. Now this same 200 horsepower motor, we talked about having a 6-turn coil as we discussed before, and if we take these same equations and we calculate those forces, we find that on the top coil side, and the top coil side is the one that always has the highest force, in this case is 0.163 pounds per inch of length of core. Now we want to compare that, just for putting things in perspective, the weight of the coil and how that coil would react if it were allowed to vibrate in an unrestrained manner. The old force equals mass times acceleration, but we have the force at 1.6 pounds per inch, and the coil weighs 0.04 pound per inch. And if that coil were unrestrained in the slot, and this force could cause it to vibrate in a free manner, the force acting on that weight or that mass would create a vibration of 5.5 mils peak to peak at 120 hertz. That's at normal full load current. The motor has 650% starting current, and we said before the forces vary as the square of the current, which means that under starting conditions, those numbers would go up by a factor of 42. The force acting the coil is now 6.9 pounds per inch, and the unrestrained coil would vibrate 0.23 inches, which is obviously not going to happen because it would be outside of the realm of the constraints of the slot. But that's just to demonstrate what those forces can do if they are unopposed by anything other than the mass of the coil. When looking at the forces on the coils acting in the slots, we pointed out that the forces acting on the top coil were greater than those acting on the bottom coil, with this ratio being about 3-to-1 difference. And this is true in all 2 coils per slot situations. It's also true, and only true, if this relationship is valid only if the coils are in the same phase in the same slot. But that same relationship exists for all of the turns in the coil. The total force is made up by the sum of the forces on each of the turns, and because of this other distribution, it is obvious that the force acting on each turn is not the same. In fact, in this case, the force acting on the top turn is about 12 times the force acting on the bottom turn, and the force acting on the top turn is about 10% greater than the force acting on the second from the top turn. But just take a look for a second at what the force on that top turn is and go through the same analogy that we did on the total coils. The force on the top turn at normal full load current is 0.0334 pounds per inch, which would produce an unrestrained vibration of 7.7 mils peak to peak at 120 hertz. But with starting current, the force would increase by the 42 ratio that we've discussed, and it would now be 1.41 pounds per inch and would cause an unrestrained vibration of over 0.3 of an inch. Obviously that can't happen because it's outside the restraints of the physical situation. But it points out that if the conductor within the shell of the insulation is given room, it will vibrate, and it will vibrate excessively and cause some of the damages that we saw in some of those initial slides. It will pulverize the ground insulation, the turn insulation, as well as the strand insulation, and cause some of the other undesirable effects that we've previously seen. So this obviously points out the importance of the selection and the bonding of the turn insulation, and it again points out why the complete impregnation of the coil with a resin of adequate mechanical as well as electrical properties is so vitally necessary. Now let's talk about the vibration of the end turns. Because the total system goes together, the end turns have to be adequately braced and restrained from excessive vibration, just like the coils do in the slot, because one without the other is going to cause the same types of problems as we've previously seen. Now, we indicated before that we have the vibratory forces as well as the DC forces, and the mechanism for controlling them is the same, and they have to be adequate for the same reasons. Let's again take a look at the coil end turn vibration situation where we have the radial as well as the tangential and the other complicated vibration mode shapes. And again, consider the fact that the end turn is a laminated beam with the copper conductors being the laminations, and if the beam bends, the laminations try to slip relative to one another, and this slippage abrades the turn insulation, produces turn failures, and we've seen examples of that. So impregnation and bonding again is important in order to control that part of the system. Now, again, just to remind you that the DC forces are also operating on the end turns, and if they are not properly restrained, they will deform the windings in a manner similar to what we saw before as shown in this picture. Now let's take a little look so we can better understand what's going on the end turns out there. These are some slides developed from some information presented in another IEEE paper entitled Mechanical Behavior of Stator End Windings, again produced by some Japanese gentlemen from Toshiba. This slide shows the typical distribution of forces on the end turn of the coil. And as you can see, it is not uniform, and because it is not uniform, it's trying to bend and distort the coil into various shapes. Below that is shown the strain distribution as would be measured on the surface of the coil when it's subjected to forces of the pattern as described above. Now, remember again that these forces are both vibratory and steady-state DC forces trying to permanently deform the coil as well as trying to make it vibrate. But by seeing that force pattern and the strain pattern, it offers some insight as to how the coil should be blocked and braced in order to minimize the vibration, in order to minimize the motion. Because if you looked at that previous pattern there and compared where you would put your blocks, if you put the block right at the point of minimum force, or a node so to speak, it is not going to reinforce the coil, and it's going to allow it to deform and vibrate pretty much as it wants to. So the location and the number of the braces or the blocks or the ties is very critical in determining and limiting the amount of vibration and displacement that coil will be subjected to. Just take a practical example and consider what we see in the next couple of slides here. Here are the end turns of an actual winding on a large machine in the 5,000 horsepower range. And note that each coil has 3 ties, 3 rows of blocks and ties, and obviously we're looking at the bore side of the coil here. And on the back side, the coils were tied to a ring, and there were 2 additional rows of blocks and ties. This was on the original winding. And the machine was rewound because of winding failures. In the new winding, the bracing was considerably different. Where there were 3 rows of blocks and ties, there is now 1 row of Dacron felt blocks. On the back side, the coils are tied to the ring, but there are no additional rows of blocks. So somebody made a conscious decision to go with a lesser degree of bracing on this winding as opposed to what was on the original equipment. Now, the original equipment had an asphalt flake mica insulation system, and this has another type of system which is not thermoplastic and is more mechanically rigid, but at the same time, the question would be, is this stiffness of this insulation system by itself sufficient to warrant the decrease in the number of blocks and ties that were used on this particular machine? Because, as you're well aware, blocking and tying and bracing is a very labor-intensive operation which requires many man-hours in a large machine or even a few hours in a small machine, and that can make the difference between the cost being within the limits of what one expects and being excessive. And sometimes decisions are made to compromise the blocking and bracing without a full understanding of the ramifications and the dangers that are being taken as far as courting the possibility of a premature failure of the machine. Now, it is beyond the scope of this course here to go into all the details of how to block and brace various kinds of windings in different types of insulation systems. But again, going back to that initial opening statement practically, that the primary cause of winding failures is vibration. It's mechanical. and it doesn't make any sense to compromise on these vital mechanical bracing characteristics, which essentially determine the durability as well as the reliability of the winding. Another piece of information from the paper that we've been quoting shows some interesting relationships between the strain actually measured at a point on the coil, as you can see as indicated at the point of measurement, and compared to the progressive installation of additional blocking. And this blocking, as you might expect, the point is being measured on the back coil side, so adding blocking to the bore side has relatively little effect. But as you start getting the blocking closer to the point of measurements and the point of distortion, you can see the strain that's produced in the coil is produced drastically. And if you correlate that with some of these force and strain patterns that we've talked before, hopefully that provides a little bit more insight into how and why a winding must be braced in order to protect it from the vibratory and the DC forces that it will experience during normal operation. So what can we do about it? Just as a reminder, the intent of the blocking is to produce an arch-bound structure so that one cannot move relative to the other. In the case we're looking at this slide here, we can see that the winding was blocked with Dacron felt, and if the Dacron felt blocking is not thoroughly impregnated with resin, or if the end-turn insulation of the coil is not solid and well-founded, then one coil can move slightly relative to the other and produce the types of things that we were talking about before with this gross displacement of coils between adjacent phases. And this can cause either immediate failure, as it has in many cases, or at least accelerate the failure process. So the blocking and bracing is very important. And the name of the game is to control the vibration in the slot section and in the end sections of the coils. We've talked about vacuum pressure impregnation and wedging and filling and the various things we need to do to control the vibration in the slot. And we also have to address the same considerations in bracing the end turns, such as shown here of using glass rope in the nose to tie the individual coils to it, or to tie the coils to double lashing rings as we show here. Surprised how many machines one will run into that have been repaired and rewound where somebody has decided to leave off the bracing rings. And maybe that's a good decision and maybe it isn't. If they were put on there in the first place, they were generally put on for a good reason. And if one doesn't understand the reason and the needs of that system, they are playing with fire by altering it without making a thorough analysis of the situation. Last but not least, the blocking and the tying and the bracing ought to end up looking in a regular, neat, workmanlike fashion. It may be cosmetic, but if the pole jumpers, as shown in this picture here, are well compacted and tied and founded, then it gives one the impression that the blocking and tying and the bracing system was well implemented. And if it's been well impregnated with high-strength resin or varnish, then the chances of it being successful are obviously greater than if it's a very loose and unworkmanlike looking situation. Now, that's about the end of it. We've talked about failure analysis and why it is so important to understand the failure mechanisms that we're trying to correct, because if we do not understand the failure mechanism and we're working on the symptoms of the problems, then we're doomed to repeat the problem because we have not directly addressed its true cause. We've talked about the primary failure mechanisms of mechanical vibration and distortion and electrical and thermal and chemical. We've talked about the importance of turn insulation, because I feel all too often this subject has been not given the degree of attention and consideration that it should have been in the past, and hopefully we've shown you the electrical and mechanical requirements that we're asking this insulation to withstand. We've also talked about the selection of materials, the wide variety of materials that you have to choose from. And the materials must be compatible not only with the requirements of the machines and the environment in which they operate at, but they have to be compatible with the manufacturing facilities and the resources that the repair shop has available. And I think we've also dwelt sufficiently on the subject of the thermal part of the equation. And again, most people use high-grade insulating materials that have temperature capability to withstand normal application temperatures, but keep in mind that there are things that can happen that can cause the machines to run at temperatures greater than the withstand capability of even these Class F or Class H materials that are typically used. And some of those may be under the control of the repair shop, and some of them may be only under the control of the user. And again, by understanding what's going on with the equipment, you can protect yourself and your customer from premature failures by pointing out what's going on and recommending the proper corrective action. And then finally, we've dwelt at length on vibration control of the end turns and the slot portions of the coils, and hopefully offered some insight into the forces and the force patterns that are operating to cause these things to happen, so that when we rewind a machine, we take a serious, disciplined look at not only the design of the coils, but also the design of the total system, the blocking and the bracing and the wedging and the filling, and all of those things that we initially indicated we included as part of the total insulation system. Because the rewind of motors and generators by repair shops is a serious business that requires a thorough understanding of the insulation systems and their application. And the selection of the materials and the procedures used is a complex decision that requires the evaluation of many variables and must be approached in a deliberate and a disciplined manner. Only in this way can the objective of quality rewinds be achieved.